Today in BE 110 we're going to derive the equation for conservation of energy in a continuum. So starting by considering the different terms that contribute to the energy, let's first write down an expression for the kinetic energy of a material that instantaneously occupies a region R in a continuum. So the kinetic energy K is 1/2 of the volume integral over the region R of rho times V dot V with respect to volume, or in index notation 1/2 rho VI VI dV. So energy is a scalar quantity and it's 1/2 mv squared. The internal energy, I, is the volume integral over R of rho times E with respect to volume, where E is defined as the internal energy density, in other words, the internal energy per unit mass. We'll discuss later what the internal energy could be. Now, from the first law of thermodynamics, we can state conservation of energy as the rate of change of the kinetic plus internal energy of the body, or of the region, is equal to the rate at which work is done by the body and surface forces, and we'll call that W dot, plus the rate of heat absorption into R across its boundary S, and we'll call that Q dot. So the rate of work done by the body forces is equal to the volume integral over R of rho times B dot V with respect to volume. So if force times displacement is work, then force times velocity is rate of work. The rate of work done by the surface forces is similarly the surface integral of Tn dot V with respect to S, or using Cauchy's formula, Nt, where T is the stress, dot V ds. Finally, the rate of heat entering the region R across the boundary S equals negative of the surface integral of Q dot N ds, where Q is the heat flux vector, N is the outward normal to the surface, and therefore Q dot N is the outward heat flux. Therefore, negative of the surface integral of Q dot N is the total rate of heat entering. So putting all of these terms together, our statement of conservation of energy becomes the material derivative of the volume integral over R of rho times 1/2 V dot V plus E, the internal energy density, integrated with respect to volume, is equal to the volume integral over R of rho times B dot V, the rate of work done by the body forces, plus the surface integral of N dotted with T dot V, so that's the work done by the surface forces, minus Q, the energy due to the heat flux. Or in index notation, the material derivative of the volume integral of rho times 1/2 VI VI plus E dV is equal to the volume integral over R of rho BI VI dV plus the surface integral over S of TJI VI minus QJ times NJ integrated with respect to S. So now, again using the divergence theorem to turn this surface integral into a volume integral, we obtain that the volume integral over R of rho times the material time derivative of 1/2 VI plus E is equal to the volume integral over R of rho times VI plus del xj of TJI minus Qj integrated with respect to volume. And now again, since the region R is arbitrary and the equations must hold for any and all regions R, then the integrands themselves must be satisfied, and therefore rho of the material derivative times 1/2 VI plus E equals rho times VI plus del xj TJI minus Qj. Now, recognizing that the material derivative of the velocity of dvi dt is ai, the acceleration, we can rearrange the equation above to obtain the following. Vi times rho times ai, which is ddt of vi, minus rho times bi here, minus del tji del xi, plus rho times dE dt, term, minus tji times del vi del xj, plus del qj del xj. Then we recognize that this term inside the brackets is actually 0 from conservation of linear momentum. This is the conservation of linear momentum says that rho times ai equals rho bi plus del tji del xi. So this term is 0 thanks to conservation of linear momentum. And so therefore our conservation of energy equation simplifies to rho times dE dt equals the stress Tji del Vi del xj minus del Qi del xi. Now Tji del Vi del xj, this term here, could also be written as 1/2 Tij del Vi del xj plus del Vj del xi, and that's because we know that the stress tensor is symmetric. And 1/2 del Vi del xj plus del Vj del xi is Dij, the rate of deformation tensor. Therefore, we can also write our conservation of energy equation as rho times the material derivative of the internal energy with respect to time is equal to Tij Dij minus del Qi del xi, or in direct notation, rho dE dt equals the trace of T dot D, this is the stress times the rate of deformation, minus the divergence of Q, the heat flux vector, where the heat flux vector comes from Fourier's law of heat conduction, which states that Q, the heat flux, is equal to minus K times the gradient of the temperature, shown here as T. So T is the absolute temperature, and K is the thermal conductivity. So this is the conservation of energy for a continuum. It includes three terms: the internal energy, the rate of work done by the stresses, which derived from the work done by the body and surface forces and was simplified by application of conservation of linear momentum, and then the rate of heat entering the system. So all that leaves is the question, well, what is the internal energy I, or the internal energy density E? And really this is a property of the material. What this statement is really saying is that as the material undergoes stress and deformation, and as heat enters or leaves it, the the net energy of the material changes. And that net energy must be somehow stored internally in the material. And we'll learn later that different types of material store their internal energy differently. For example, crystalline solid materials like metals, for example, tend to store their internal energy as the energy between the bonds of the crystals. Whereas rubbery type of materials, like rubber, actually store their internal energy as entropic energy. And so applying stresses to a crystalline type of material increases the internal energy between the bonds of the material, whereas applying stresses to a rubbery material actually increases the internal energy by decreasing the entropy of the system, by making the disordered, tangled fibers less disordered and therefore having less entropy.